Okay, in this video we're going to be looking at how to use the net change theorem. The net change theorem says that the integral of a rate of change of a function, capital F, is the net change of the function, capital F. That is, the integral from a to b of capital F prime of f of x dx is equal to f of capital F of b minus capital F of a. Recall that this just comes from fundamental theorem of calculus part 1, and that stated that if we have the integral from a to b of this continuous function f of x, that this will be equal to capital F of b minus capital F of a, where capital F is the antiderivative, or any antiderivative, of little f. Since capital F is the antiderivative of little f, that means that capital F prime of f of x is equal to little f of x. So that is why that is where this comes from, because all we do is replace little f of x with capital F of x, giving us the net change theorem. So pretty much, if I want to find the net change of a function, I integrate its rate of change. We can apply that to position and velocity, because if I want to find the net change of position, then I integrate the rate of change of position, which is your velocity function. Now, because an object can move forward and backwards, if an object is moving backwards, it will cancel out some of the forward movement. So if a function can move backwards, or does move backwards, and we want to find the total distance, we integrate the absolute value of velocity to make sure that all the negative values of velocity are added with the positive values of velocity, giving us the total distance overall. That is illustrated in this diagram. As you see here, here's my velocity function. So we have these positive values of velocity. This is when the object's moving forward, and then the negative values of velocity. This is when the object is moving backwards. And so these values of moving backwards are going to cancel out some of this. So that's not going to. So if we don't think about that and we just integrate, then what happens is that we don't get the true total distance, because these will subtract away from the positive values. So that's why we take the absolute value of the function, and when we do that, then this portion of the curve, it will reflect, right, if we take the absolute value of the function. So then, now these values of position that would have been negative are now positive. So if we add up all the position values, then everything adds up together, nothing subtracts away, and then we get the total distance. So that's the point of absolute value here, to get the total distance. All right, now let's see how this works. So if in this question I'm given the velocity function, I'm given the interval on which I want to find the displacement and the total distance. All right, so for displacement, let's integrate the function. Okay. So now finding the antiderivative, we are going to get t cubed over 3 minus t squared minus 8t, and then we're going to evaluate that from 1 to 6. And when we do that, we get negative 10/3. So that will be the displacement. All right, and so this displacement is helpful because at least now we know our position, right? So in reference to our starting position, we know that we are negative 10/3 units behind that, right? So that's where we end up at overall. Now, if I want to find the total distance traveled, what I would need to do first is find when velocity is 0. So I would set the velocity function equal to 0, factor it, or just solve for t. In this case, I can solve by factoring t minus 4, t plus 2. And so t would equal 4, or t would equal negative 2. Now, because we are looking at the interval from 1 to 6, I don't have to worry about this value, I just worry about this one. And then, as we normally do with number lines, we're now going to pick, this corresponds to velocity. We're going to pick some test points in between each one. So if, let's say t equals 2, then this factor will be negative, this will be positive, so velocity will be negative. And if I pick t equals 5, then this becomes positive, and this is also positive, so it's positive here. So we see that velocity will be negative on this interval. So that means that the particle is moving in reverse here. So we want to make those values positive, so we're going to take, when we write that part, so here's how it sets up, so the distance. So on this interval, we're going to go from 1 to 4, and because velocity is negative on that interval, I'm going to put a negative on the outside of that. And then what that's going to do is it's going to make all of those values now positive. So now velocity will be positive because of this. And then I'm going to add to that the other interval, the integral from 4 to 6 of the function t squared minus 2t minus 8. So we compute the integral here, the antiderivative. When you compute it, it'll be the same as the other antiderivative from the first part, but the negative will distribute through that, changing the sign, so the antiderivative will be negative t cubed over 3 plus t squared plus 8t from 1 to 4. And then this one will be the same as that one. So, oops, sorry. And so for that one we get t cubed over 3 minus t squared minus 8t from 4 to 6. Okay, and we do the computations there, and the computation that you will get, I believe, is 98 over 3. All right, so that is how you find the total displacement and total distance traveled by a particle.